we'll be solving LeetCode's number 200 problem, which is called number of islands. It's a medium difficulty problem, and it's, in my opinion, it's commonly given as an interview question. If not exactly the same problem, then a kind of a variation of this problem can be given, because it introduces it can be solved. The problem can be solved using breadth first search or depth first search approaches, which are commonly used, and in my opinion you should be familiar with both of these two approaches. So in the previous video we discussed a different problem and we used depth first search approach. So in today's video for this problem we will be applying breadth first search or BFS approach. So let's quickly read the description. So given an m times n 2D binary grid, which is called grid, which represents a map of ones and zeros, where ones represents the land and zeros represents the water. So return the number of islands. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. So this part is very important to notice. So an island is connected with adjacent lands horizontally or vertically only, but not diagonally. You may assume all four edges of the grid are all surrounded by water. So here we have two examples, so let's quickly go through them. So in the example 1, you can see this is the grid, and as it's said here, we can assume that this grid is basically surrounded by the water. So if you see here, there are some ones and zeros, but all ones are connected to each other directly or indirectly. So basically this one is connected to two other fields, one horizontally to this one and one vertically to this one. This one is connected to three nodes or three fields, etc. And we can see that all of them are forming a single island. Having said that, in this particular case the output should be 1. Why 1? Because there is a single island formed of all of these ones here. In the second example, again we have some ones and zeros. These four ones form an island because they are connected horizontally or vertically, but this one here is not connected to any piece of land, so because it cannot be connected diagonally, and if you look horizontally or vertically, it's surrounded by the water, and because of that this one is a separate island. And similarly these two ones are also surrounded by the water, meaning that we have three disconnected islands here, and because of that the output will be 3 in the second example. So yeah, given an m time as an input, we are given an m times n 2D binary grid. So let's quickly go through the constraints. M is the number of the rows basically in this input grid. So here it's 4, and n is the number of the columns. So it says for any I, the length of the ith row will be equal to n. That means basically that if the number of the items in the first row is 1, 2, 3, 4, 5, then all other rows will have the length of 5. So it's not possible to have the first row with length of 5, the second with the length of 4, for instance, or 6 or whatever. So it's m times n grid. So we can assume that that's always true, or otherwise we can simply create a kind of a validation method that would check whether this constraint is satisfied. We won't do that today in today's video, but yeah, if you want to add that extra check, please feel free to do that. And m and n are both integer values between 1 and 300, so they couldn't be 0, and all values provided in the grid of this char matrix are either 0 or 1. So we can assume that is always true. However, yeah, if you want, you can relatively simply add a check and make sure that it only contains zeros and ones. Let's see how we can implement the solution to this problem. So basically the solution to this problem will be we can simply use the BFS or DFS approach. DFS approach or depth first search approach was explained in the previous video. So in today's video we will see how we can implement a different way to traverse the nodes in a given graph, which is called breadth first search. And breadth first search approach is also quite commonly used. And if you're preparing for a coding interview, I think it's very important to be familiar with this approach. So BFS or breadth first search is naturally an iterative algorithm, unlike to the DFS or depth first search, which is naturally a recursive algorithm. Breadth first search or BFS works as follows. So it starts with a node and it naturally goes in breadth instead of depth, which is the case with the DFS or depth first search. So it would start, for instance, with the node 1, and it will naturally mark it as visited, and it will naturally iterate through its adjacent nodes first and mark them as visited. So what nodes are adjacent to this item here, to this node here? Well, there are two nodes, this one and this one. So it will naturally mark them as visited first, and it will continue with adjacent nodes of these two nodes. So let's say that it first visits this node and then this node, and then it will start with adjacent nodes of this one, which is this one and this one. Also, to keep track of the nodes that are going to be visited next, BFS uses a data structure which is called queue. And why queue? Because the queue has the ability, basically follows the approach first in, first out. So when we can add values to the queue, but when we want to take a value from the queue, the first value which will be taken out is the one which was added first. So that kind of a structure is suitable here for this BFS approach. So I'm gonna explain this in more details once we start implementing the solution. And one more thing to notice: BFS or DFS approaches, when we iterate through the nodes using these two approaches, they will work as follows. They will iterate through all of the nodes which can be achieved from the starting node. So the graph needs to be connected, so we can traverse all of these nodes with a single DFS or BFS iteration. So if we apply BFS in this particular case, we will traverse through all of the nodes, all of the ones. When I say nodes here, the graph is represented with the nodes of the graph are represented with ones. We need to go through the nodes, through the items with number 1. So we need to traverse all the ones using BFS approach, and it will go through all ones which can be achieved from the starting node, meaning that the graph needs to be connected. So if we traverse the node, so if we start from the first node, we can go through all of these nodes because they are all connected. But on the other hand, if we would run a BFS algorithm starting from this node, it will iterate through these 4 nodes only, and it will end there, but the other nodes will remain unvisited. Given that we need to count the number of islands, what we could do, we could run BFS multiple times until we mark all nodes as visited, all ones as visited. The number of times we run the BFS algorithm will be equal to the number of islands. Here we will, with a single BFS run, we will iterate through all of the ones, so the output will be 1, but here we will need to run BFS 3 times, so once for the first island, for the second time for the second island, and third time for the third island, and that's why the result will be 3. So let's see how we can implement this. So this is the method that we need to implement. So I'm using Java programming language, but yeah, you can quite easily transform this code to any other language. So as an input we have the grid. The grid contains ones and zeros, so maybe, yeah, we can say if grid is equal to null or grid.length is 0, we can throw an exception here, illegal argument exception, provided grid must not be empty or null, something like that. So if you are going to submit this solution to the LeetCode portal, so there is no need to add these checks, because it will run the solution against the test cases which assume that this is always true. So there's no need for these checks, but yeah, it's always good to add this extra check, especially if you are preparing for a coding interviews, so the interviewer might pay attention to these details, and maybe these constraints won't be given. So it's very important to read the constraints, or if you are attending an interview, to clarify with the interviewer that about the constraints. You can simply ask, can we assume that the grid is never going to be null or the length, or do you want me to add the check, etc. So I added this check, but I'm not going to add the checks for all of these things here, because it will just make the code more complex, and I don't think that's very useful here, because we want to focus on the BFS approach. So how can we do this? So what we can do, we can simply use this grid, and how can we mark that a node is visited? So going back to this, 1 second. Going back to this example, So here, once we visit a node, what we can do, we can simply change the value of this 1 to 0, and by updating the value of a node from 1 to 0, that way we can mark it as visited. That way it won't be visited again. The reason why I decided to use the provided grid and to modify the values within the grid is because we just need to return the number of the islands, and because of that we can modify the values in the grid, and that way we don't need to create an additional structures, and the overall solution will be memory efficient. So that's why we can use that approach to mark visited node as visited by setting the value by updating the value from 1 to 0. So what we can do, we can simply go for each value in the provided grid, while e is less than grid.len, e++, and so this is the way to traverse the matrix, provided matrix, while j is less than grid of 0 or grid of I, doesn't matter, .len, j++. So what can we do here? So for each node value, we can simply check if grid of ij is 1, meaning that it's not visited. We can simply say run BFS starting from, for the provided grid, started from the node aij. Okay, we will implement this BFS. An alternative way would be to run DFS. So in today's video we will be implementing the BFS solution, but yeah, maybe you can do the approach with the DFS solution. So you can simply implement the DFS approach. And what will this BFS do? Well, it will try to visit as many nodes with the value 1 as possible, starting from the ij node, and it will update the values in the grid to 0 for all visited nodes. So going back to this example, when we run BFS from here, it will visit all the connected nodes and change their value to 0. And there will be no ones left after a single iteration of this BFS call. But also we need a kind of an input, a counter that will count the number of the islands, so we can call it num of islands, which is initially equal 0, and that should be returned at the end. Okay, so once we reach a node which is unvisited, we can simply increment this number of islands. So what we need to do, we need to create this BFS method. So yeah, I'm gonna remove this DFS, so we will be using breadth first search approach. So how can we do this? We can create a method called BFS, public void BFS, which takes the grid as an input, which is called grid. Takes this, also it takes the coordinates of the starting node, which we can call int x, int y. So xy is the coordinate of the starting node, and yeah, and here what we can do, we can simply say call BFS for the grid starting from I and j. What it will do, it will visit all the nodes, all the ones that are connected to this ij node, and it will change their value to 0. So in the next iteration, those connecting nodes won't be picked up, and we will run BFS basically only for that many times to cover only disconnected nodes, only to count, basically to count the number of islands on the grid. So using the first example, here it will be executed only once, and it will change the values of these ones to 0 in one iteration of the BFS. But in this example, it will be executed 3 times, because it will first be executed to cover the first island, then to cover the second island, and then to cover the third island. Okay? So let's quickly implement this BFS approach. So how can we do this? So first, let's see if you check the, let's say we start from this node, or we start from this node, somewhere in the middle. So we can go in 4 possible directions. One is to go 1 step up, the other one step down, or 1 step right, to the right, or to the left. So we basically have for every single node, there are 4 potential directions. So, and how can we, so if we want to jump from this point to this point, we will remain on the same column, but we will go to the row which is equal to the row of the current node minus 1. This one is the same column, but the row will be the current row plus 1. So there are 4 combinations of potential moves, and we can create, for that purpose, we can create a constant which will be called private static. It will be like basically a matrix of the direction, so we can call it dir, like directions, which is equal to, so we have 0, 1, 0, minus 1. So we are remaining on the same row, but we are going 1 step to the right or 1 step to the left. Then we have 1, 0, and minus 1, 0. So this one is to the right, to the left, 1 step down or 1 step up. So here, how can we implement this? So at this point, we said that we will be needing a structure which is called queue. In Java, queue, there is a an interface called queue, and in queue we will be using the coordinates of the nodes that will be visited next. So basically it's the queue of the nodes that will be visited next. Coordinates, so for the coordinates we can use an array of integers which will always have the length of 2, one for the x coordinate and the other value for the y coordinate. So we can say something like this: a queue of integer arrays, which is called queue. And in Java there are multiple implementations of the queue. I will be using the most commonly used one, which is called linked list. And queue has basically two important methods that we will be using. One is to add to the queue. We can use add or offer. And the other one is to take the value from the queue which was added first. That method is called poll. So we will be using add and poll methods to add or to retrieve the value from the queue. Okay, this is the queue, and here we are called with the, this is the shared grid, I mean the reference to the grid, which we will be used to update the values and to see basically to traverse the nodes, the nodes, yeah, in the connected graph, in a connected component. So here we know that x and y node is 1 because it is called from here, and before it's called there was this check. So what we need to do, we need to say that the grid of x, y is now marked as visited. So I'll add a comment here, mark xy node as visited. Okay, and then we will add this node to the queue. Okay, and how can we traverse, how can we implement BFS? Well, basically we can do something like this. While queue is not empty, we will take the current node, which or the node which was first added from the queue. So we can call this current, which is equal to queue.poll. And then what we need to do, we need to go through all adjacent nodes of the current node and to add them to the queue. So we don't need to add the zeros, so because that's the water, but we need to add the land values, which are basically, which will have the value 1. So how can we do that? Well, how can we reach to the adjacent nodes of this current? Well, we can simply add these values from these directions. So we can do something like this: for each direction in the dir, we can say something like this: this is the new node is equal to current new int of 2 and new node of 0 is equal to the current node of 0 plus direction of 0. So, and new node of 1 is equal to the current node of 1 plus direction of 1. So we can do something like this. But there is a potential problem here. When we need to check whether we are still on the grid. So if we are looking for the adjacent nodes of this node here, so we can't go to the left or to one step up because we will exit the grid. So we need to make sure that we are still on the grid. So we can say, instead of doing this, we can set something like this: int new x is current of 0 plus direction of 0, and int new y is current of 1 plus direction of 1. And then we can check if new x is greater or equal than 0 and new x is less than the grid.len, and similarly new y is greater or equal than 0 and new y is less than grid of 0.len. And additionally, so this is new x, new y is are the coordinates of the adjacent of an adjacent node, and we need to make sure that we are on the grid, and additionally whether the adjacent node is a piece of land. If it's not, yeah, we can also skip it. So and grid of new x, new y is 1. So only in this case we will add this node to the queue so it can be visited. We will visit the node and we will add it to the queue so we can traverse its adjacent nodes later. So we can say grid of new x, new y is 0 now. Mark this node as visited, and we will add it to the queue. Queue dot add new integer of new x, new y. Okay. Some may ask, why do we need to do this now? Or can we mark the node as visited once it's pulled from the queue? Well, we can't do that because that way we may end up adding the same node a couple of times in the queue, so the time complexity of the solution will not be optimal. So it's important before adding a node to the queue that we first mark it as visited and then to add it to the queue. So, and that way we will make sure that this node will never be added to the queue again, because this condition here will not be satisfied. If that was not the case, multiple adjacent nodes will share some nodes. Will have some adjacent nodes in common, and all of them will be added to the queue multiple times, and that's why that solution wouldn't be optimal. This way, when we mark a node as visited before adding to the queue, we are making sure that it's not going to be added twice or more than once to the queue. And basically this should be the solution of this BFS approach. So we will visit all the, so this way, starting from the XY, we will iterate through all adjacent nodes of the, and through all of the nodes that can be achieved from the start node. We will mark them all as visited, and that way we will basically eliminate an island from the grid. And this BFS here will be called for every single island. For every single island exactly once. And that should be the solution of this problem. So let's quickly try this solution to see whether it works. So here I already added these two grids. One is the grid with a single island, and the second grid is the grid with the 3 islands. So yeah, let's quickly try to call this solution. Solution is equal to new solution, and we can say something like this: result for the grid 1 is solution.num islands grid 1, and similarly for the second grid. So for the grid 2 is number of islands for the grid 2. So let's call this. And yeah, as you can see here, result for the grid 1 is 1, result for the grid 2 is 3. So this solution seems to be working fine. So before we end this video, let's just quickly discuss the time complexity of this approach. Well, here if we see here, we will iterate through the whole grid and call the BFS. So if m is the number of the rows and n is the number of the columns, the number of times this if statement will be called m times n times, and for this BFS it will visit all the ones exactly one time. So because before we add a node to the queue, we mark it as visited. So every single node here, every single node will be visited exactly one time. Having said that, the overall solution of this problem has the time complexity of m times n. So time complexity of the solution is big O of m times n, where m is the number of the rows and n is the number of the columns. So again, why is m times n? Because we visit every single node exactly one time. So we are not going to visit it more than that. Additionally, regarding the memory complexity, so here we use an additional queue, but we don't keep track of the visited nodes in a separate grid, because we are not asked to print the islands or something. We are just, but even that we might not be needing, but we are just asked to provide the number of the islands on the grid, and because of that we are not using allocating an extra space for some additional data structures to keep track of the visited nodes. But the only extra memory that we are allocating is for this queue, and this queue will never have the length longer than the number of the ones. And if the number of the ones can never be greater than the number of the elements of this grid. So having said that, the memory complexity of the solution will be big O of, again, m times n, which is used for the queue in the worst case. That would be all for this video. I hope that you liked it, and I'll see you in the next video. Thank you.